Hello, everyone. I wanted to get us kicked off by going through some basics of predictive analytics. And I think it's important to sort of go through some of this stuff before you start reading the Siegel book. The Siegel book does a really good job of sort of kind of talking about a more global approach towards predictive analytics and a number of different ways that we can use predictive analytics, but he kind of skips over some of the basics. And so I want to go through that and make sure that you have a clear understanding of just the demystified process of predictive analytics before you read his book. So let's talk a little bit about prediction and what he means by prediction, what we all mean by prediction when we talk about predictive analytics. Prediction is really it's not mysterious. It sounds mysterious, but it's not. There's actually more math involved than magic because we're actually using mathematical models. We're going to build several of them actually throughout this course. You'll build several mathematical models that will allow you to make, and probably a better word instead of prediction is estimates, but prediction is the word that's stuck, so it's the one that we'll probably stick with as well. But when we think of prediction, we oftentimes we think about looking into the future and what's going to happen in the future, and we have to kind of question what's our guide. Whenever we look in the future, what are we basing any sort of projections about the future events on? And in order for us to get accurate results, we can't just look in the future without anything to guide us. So prediction in predictive analytics uses actually the past. We look at the past to try to determine what are going to be future likely outcomes. So how does it work? Well, in its simplest form, we look at past data. So we might look at sales records or medical records or sports records, etc. And we look at relationships between variables in past data. The idea being that if two relationships or two variables were related in such a way in past data, they're likely to be related in a similar way in the future. So we look at variables that might be related, like age and sales, weight and blood pressure, or in sports, home run and the height of the player. And we look at these variables in past data, and we calculate a relationship between them. So we look at a couple of key values, and we determine from using some mathematical processes, which are a lot simpler than you might think, we calculate what the relationship was in the past between those two variables. Then we fast forward into the future and we use the model that we've built, the mathematical model that we built that considers the two past variables, and we use it to apply to situations where we might only have one of the variables. For example, we might have the input variable, but we don't know what the output variable is likely to be. So that is what we're doing with predictive analytics. We are looking at the past, we are determining a relationship between variables, then we are fast forwarding into the future, and we are applying the mathematical model we built to situations where we only have the predictor variable. So you see, there's really no magic involved here at all. So there are two types of variables in predictive analytics. The one, I've already referred to them by their names a couple of times, but the one type is the predictor variable, often referred to as the independent variable. And those are the variables that we're using to make the predictions, right? The predicted, oftentimes called the output or the dependent variable, is the variable that we are predicting, okay? So it's kind of a little confusing because predictor, predicted, but really when we're looking at a relationship with a simple linear regression where we're using one variable to predict the output of another variable, we are simply using the predictor variable to predict the predicted variable, okay? And they'll become more clear to you as we start building these models. But again, we go into the past, we look at the relationship between the predictor and the predicted variable, we build a mathematical model, and then we fast forward into the future, and we use the predictor variable to predict new values or new estimates for the predicted variable. So let's look at an example, okay? Imagine customers shop at Fred Meyer. And they use their loyalty cards or their loyalty numbers, and they use them. They've got an incentive to do that because they get special deals on gas and stuff like that. So Fred Meyer tracks all of the things that each customer buys. They also have information about their customers when they filled out their loyalty card applications, things like their birth date, so they can calculate the age of the customer. So what we might be asking ourselves is there a relationship between the age, in this case that would be the predictor variable of the customer, and their monthly average spending, and that would be the predicted variable. So if so, can we calculate this mathematical relationship? And if we can calculate that mathematical relationship, can we then use it in the future to determine how much a 45-year-old is likely to buy on average each month? And the other thing we have to think about, and this is the first time I'm bringing this up, but we want to look at how accurate is our model. Some models are accurate, some models not so much. So anyway, that's just one example. And here's another very famous example. This is kind of the birth of predictive analytics. So Dolbear's crickets. Dolbear was somebody in the past. I don't know exactly who he was, but he kind of was a grandfather of linear regression. Anyway, he listened and tracked the number of times a cricket chirped each minute. And he determined that it changed. The number of cricket chirps changed. And so he looked for some sort of cause for why it was sometimes faster and sometimes slower. And he finally landed on temperature. So he compared the cricket chirps to temperature and was able to find a fairly linear, fairly predictable relationship between the number of chirps and the temperature. The warmer the temperature, the more chirps. So he used past data. He tracked chirps and temperature over periods in the past, and he used his past data to build a mathematical model that compared temperature and chirps so that he could then, in the future, take a look at the number of chirps and determine with fairly good accuracy how warm it was outside. So here's a diagram that kind of shows a little bit about what's going on under the hood of a predictive analytics model. So on the left side there, we have old data, and we have known variable 1, which is our predictive variable, and we have known variable 2, which is our predictive variable. And when I say known, it means we know the values of them. So we may have 100 instances, we may have 1,000, we may have 5,000. So we have 5,000 instances of variable 1 and 5,000 instances of variable 2, or however many we have. And we use that data to feed into the process of building a predictive model. Okay? So we want to know what is the relationship between variable 1 and variable 2, or the predictor and predicted relationship, or variables. What is that? And we use that information to build a mathematical model that we can then use for future data in the scenarios that are over there on the right. Now, the double-headed arrow is important to note because now we're in the future and we're looking at new known variables. So we have new known variable 1, we have new known predictors, okay? And we have that list, and we take those variables and we feed them back into the predictive model. And when we feed them back into the predictive model will output predicted variable 2. So our best estimates for each instance of variable 1, what is the predicted variable 2 likely to be? And that's really what the predictive model is all about. If we use Dolbear's old data was comparison of temperature and the number of cricket chirps per minute. So we fed that in, or he fed that into and built a predictive model that could determine the relationship between temperature and chirps. Okay. In the future then, when he was able to track chirp counts per minute, he could feed that back into the predictive model, and the predictive model would spit out an estimate or a predicted temperature. And what he found is it was reasonably accurate. So let's talk a little bit more about old or past data. Okay, what we're looking at here is they're like records that we gather every day. So we have sales records, medical records, things like search engine searches, those kinds of things. There's an amazing amount of data that is gathered every day. And in the Siegel book, you'll read a little bit more about the volume of data that's being gathered every day. So we analyze this data to see if we can find meaningful relationships between any of the pieces of information that we're tracking. And when we find meaningful relationships between things that we're tracking, we can build models. And we build models that will allow us to capitalize on those relationships. So we apply, and then later on, we apply those models to predict future behavior. Now, the issue that Siegel brings up so much in chapter 2, and I don't want you to lose sight of it because I think it's important, but I think it's kind of a little beside the point of what I want to cover in this class, and these get down to privacy issues. So he brings up a whole lot of issues about things like who is gathering your data, what are they using it for, and to try to get you to think about, do you approve of these practices, and do you even know what they know about you? He uses the famous Target example, and I'll let you read that in chapter 2, to cite how the media has jumped on this and really is looking at it as kind of an invasion of privacy. If all these companies are tracking all this information, how safe is our privacy? I think what we need to think about, though, is that the companies are going to track this information regardless. I mean, they're doing it now. They have legal right to do it. We all, in various forms, one way or another, when we're asked or when we need to be asked if it's okay for them to track our data, we give them that authorization by signing up or clicking on a EULA or clicking on something else. So they're going to track this information regardless. That's really where the privacy issue lies. Where a smaller privacy issue might lie is how are they going to use it to make predictions in the future? So how are companies making predictions about what we're likely to do? And then the other piece of this, which Siegel also talks about in chapter 2, is to what extent are these accurate? And to what extent can they make accurate predictions about what our likely behavior is going to be going forward? So it'll be an interesting conversation, and we'll touch on some of these things when we get to that. But I think it's important that we recognize that pretty much in this class, we're going to look at what is predictive analytics, how can it help companies, and then when we get into the Python piece, I'm going to show you in Python how to actually build these. Let's talk a little bit more about past data for models. I'll do another presentation that talks in more detail about this because you're going to be asked to deal with different types of past data. So the three categories of past data that we'll work with, the first one is training data, what we call training data. And that's data, remember I referred to the 100 or the 500 or 5,000 records in the past data set. That's data that we use to actually train our model. You can substitute the word train with the word build, to build our model. So train or build in this instance pretty much means the same thing. So the training data is what we use to build our model. Now, we also break off a chunk of that training data. Maybe we pull out 10,000 records and we use 7,500 records to train the data and 2,500 records to validate the data or validate the model. The reason why we use validation data is we want to be sure that we don't overtrain our model. Now, we can make tweaks and we can make adjustments to our model when we build it. And if we make too many tweaks and too many adjustments, our model will be really good, but it will be really good for our training data. So that's what we use validation data for, because it's of a certain type. It's similar to our training data, but it's not part of the training data set that was used to build the model. So we should be able to run the validation data through the model that we built and get a predictable and consistent result. If we don't, if something's very, very different, then it could be said that we overtrained our model on our training data set. The other piece of data that can be used in building models is test data. Now, test data can be in a similar format, but it comes from a different source, right? It's not part of the original set that we broke into two pieces to create the training and the validation data. It comes from a completely different source. And it can be used to make sure that our model still responds in ways that we want before we ever deploy our model into actual production use. So why all the validation and testing? Well, because no model is 100% accurate. Remember, what we're doing is we are predicting or we are estimating. Some would say we are guessing, but it's a very educated guess because we're looking at relationships between variables and past data. But no model is 100% accurate. And because they're estimates, they have error. And let's talk a little bit about error. What do you mean by error? Well, when we build a model, we use it to make predictions. And as I indicated, those are just estimates. And we might be off from what the actual value turns out to be. So the amount that we are off is commonly referred to error. And this is kind of a misuse of the term because error assumes that we made a mistake or that maybe our code is wrong or our model isn't very good. No, none of that applies here. What error is the difference between what we predicted and what actually happened. So we, of course, want the error to be as small as possible. It is unlikely that we will ever, probably impossible, that we will ever create a model that turns out to have zero error. We will always have some error, but we want it to be as small as possible. And so some models do return very little error. Their predictions are very close to the actual values once the actual values become known. Other models, not so good. So we have to be very careful about what we do as far as deploying a model and how much we believe in what the model is telling us. And we'll go through examples where we will create models and then we will apply the models and we'll look at the difference between the actual and the predicted values so we can determine what the error is. And then we'll aggregate and summarize that error to know how good our model is. So a common way to calculate error is to go back to the past data. Now, remember, we used the past data. We knew the relationship between the predictor variable and the predicted variable in the past data because we had both values. So then we built the model, and now we're set to apply the model to future data. But if we go back to past data and we apply the model we created back to the predictor variable, how different is what comes out of our model from the actual value we had in the predicted variable? And that's one way to determine how accurate our model is. And we'll do some of that work as we go through building our own models. Another word for error is derivatives. So you may hear that. It's probably a more useful word to use, derivatives, simply because it means something very different. Where error can be confusing, derivatives would not be. But most of the time you hear the word error being applied to predictive models. It just means the same thing. Derivative is just the difference between prediction and actual. And there are actually a lot of ways to assess model quality. There's some statistical measures that we'll get when we run through some of this, and it will give us some values, and we can look at those values and we can say, okay, looks like a pretty good model for reasons that we'll talk about when we get there. But error is probably the simplest way to be able to do that, but there are a couple other ways that we can use to determine whether a model is good or not. So later in the class, we're going to talk in more detail about prediction and predictive models. And I'm going to have you go through a little bit of the Siegel book first, and then I want you to take make your way through the two modules, the two data camp modules that introduce you to Python, and then do some intermediate Python. So as we go through some of the work we do in Python, we'll start to look at things like linear models, and I'll explain it that when we get there, what is a linear model and why are we using it. There are two types. We'll do simple and multiple linear models. From these models, we'll come up with values commonly referred to as intercept and slope, and I'll explain to you what those are. I'll show you how you can apply the linear models that you build. We'll also take a look at something called logistic regression. So we'll look at logistic models that actually help us predict the likelihood of an event occurring based on certain predictor variables. So in those cases, the predictor variables are things we know about the data set. The predicted variable turns out to be on a score or a scale of 0 to 1, with 1 being it's absolutely going to happen and 0 being it's absolutely not going to happen. We predict the likelihood of an outcome based on the inputs. But for now, we're just going to look at some basic concepts about predictive analytics. I wanted to give you one more example too, and this is a much, much more complex regression model. And this is the company Zillow, and they're located out of Seattle. And what they do is they actually take in information about properties, and they predict what a likely sale price would be for that property. And this is just a complex regression model. So they will take in things like the size of the house, the age of the house, the neighborhood, what prices houses are sold that are close to the house, any amenities, anything that would be of value to a buyer. And they mix all that up and they use it in a great big complex regression model to come out with a value, a predicted value for the price of your house. So they have a very complex model. And they've spent many, many years and a great deal of brain power perfecting this model. But it just gives you an example of how, and this is probably a pretty complex example, but it gives you an example of how predictive analytics can be used in the real world. And Siegel gives you many, many more examples of how it can be used and can be put into practice and shown to provide real benefit to companies. So anyway, that's just one example. But despite all that I've said, I want you to remember as you read through Siegel that when we talk about predictive analytics, we are talking about the process of selecting variables of interest. They are predictor variables and predicted variables. We look at old data to see how those variables have been related in the past. Okay? And then we build a model that is derived from the relationship between the predictor and predicted variables in the old data. And we fast forward into the future and we apply that model to new data in situations where we only have the predictor variables so that we can make estimations about the predicted variables. So this will be helpful as you read through Siegel. Just remember that as he talks about predictive models, this, going back to old data, finding the variables, understanding the relationship, and then fast forwarding to the new data and applying those relationships to new data to make predictions about it, that is what he's talking about over and over again. Okay. All right. Happy reading and happy coding. I'll see you in another video.